Okay, good day. This is pre-calculus dual enrollment. I am Mr. McCulley, and this is lesson number 8, the fundamental theorem of algebra. Let's get right to it. So today, this is the book or text reference is going to be section 2.5, and our goals are going to be use the fundamental theorem of algebra to determine the number of zeros of polynomial functions. That's actually very easy, and one of the quickest parts of today's lesson. We're going to talk about finding zeros of a polynomial function, including complex zeros, and we're going to talk about finding conjugate pairs of complex zeros, a topic that we talked about in the last section, and also finding zeros of polynomial functions by factoring. So let's get through some of these notes. The fundamental theorem of algebra is this: if f of x is a polynomial function of degree n, where n is greater than 0, then n has at least one 0 in the complex number system. And from that, and when they say at least one 0, they mean that that 0 could be the same or repeated the same number of times as the degree n that we have here. And so the linear factorization theorem comes from that, and that says if f of x is a polynomial of degree n where n is greater than 0, then f has precisely n factors where n can be written as a sum n, some constant. Now a sub n is just going to be some constant value times x minus c1 times x minus c2 times x minus cn. And this, remember, this n and that n are going to be the same, so you have the exact same number of linear factors in the complex number system as the degree of the polynomial. And so if for instance, what that says, the linear factorization theorem says that if you have a fourth degree polynomial, you can come up with 4 linear factors in the complex number system. Now, some of them may be whole or completely real numbers. Some of them may be completely imaginary numbers, and some of them may be or just a full complex number. So some other notes: complex zeros come in conjugate pairs if the original function has all real coefficients. That's going to be very important later on. And a polynomial can be written as a product of linear and quadratic factors with real coefficients where the quadratic factors have no real zeros. This factorization is said to be irreducible over the real numbers. So there are instances where they just want you to find the real zeros or to factor to irreducible over the real numbers, and you'll be left with a quadratic that is probably going to be a product of 2 complex conjugates. Remember complex conjugate pairs of complex numbers. Remember, if a plus bi is a complex number, then its complex conjugate will be just a minus bi. And so again, just as a real quick example, just to reiterate from the last lesson that we have some simple errors that some students in the past have made. If I say my complex number is -2 plus 3i, then its conjugate is going to be -2 minus 3i. And notice that the -2, this value doesn't change. The only thing that changes is the number in between the real part and the imaginary part. Okay. On to examples. So we have a couple of examples. Page 340, number 28, given the function, and it looks like I forgot to write that function out. So let me do that right now. F of x is equal to, let's see here, x the fourth, and then it is plus 29x squared, and then it is plus 100. So it says write this as a product of linear factors, and so I should also say include complex factors. So we'll want to do that. And so I look at this thing here, so I'm just going to, and then we're going to verify with the graphing calculator if possible, and then we won't be able to do our complex factors with the graphing calculator if they come up. So we'll see how we get here. So I'm looking at x to the fourth plus 29x squared plus 100. Now, we're going to set this equal to 0 so that we can find the factors. We're going to find the zeros and then write it as factors. But I look at this thing and I see something that is of quadratic form. Quadratic, I spelled that wrong. And since it's of quadratic form, and there shouldn't be a little, I don't know why that line's there. Okay. Since this is of quadratic form, we could use the quadratic formula on it, but again, since the leading coefficient is just 1, I'm going to ask myself a quick factorization. So we're going to try and factor this. And I ask myself, are there two factors of 100 that have to both be positive, because I got two plus signs here, that are going to add up to 29? Well, that's easy. 4, oops, I don't know why I put x. 4 times 25 is equal to 100, the two factors, and 4 plus 25, that's going to be 29. All right, so I can go x squared plus 4 and x squared plus 25 and set that equal to 0. Now, just to kind of review back to this thing where it says it's irreducible over the real numbers, this set of factors right here, these two factors are quadratics that are irreducible, excuse me, let's get that right, that are irreducable over the real numbers. But we didn't do that. We want complex factors, and we want to get the linear factors. And since this was a fourth degree polynomial, we actually have to have four factors, and they'll all be complex numbers. Actually, they'll be pure imaginary, but that's besides the point. So how do I figure out these things? Well, we could factor it. Let's just find the zeros. And so to find the zeros, so I'm going to set each of these equal to 0. Go x squared plus 4 equal to 0, and x squared plus 25 equal to 0. Now you'll notice that there is no linear term in either of these two factors. And so you could use the quadratic formula, but I'm not going to, simply because there's no linear term and the leading coefficient's 1. So we'll go x squared equals -4 and x squared equals -25. X will equal plus or minus the square root of -4. Will equal plus or minus the square root of -25. And so each of those, the first thing, that's not a very good 4. Each of these, what we'll do is we'll get rid of the negative first. And so we'll have plus or minus I square root of 4, x equals plus or minus I square root of 25. And so from that, we can say that, let's see here, square root of 4 is 2, the square root of 5 is 25, or excuse me, said it again, square root of 25 is 5. And so we'll have x equals plus or minus 2i and plus or minus 5i. These are the factors. No, they're not, sorry. These are the zeros. And we want to get factors. So our factors will just be, well, we'll say f of x equals f of x, the function written as a product of linear factors, x minus 2i, x plus 2i, x minus 5i and x plus 5i. Now here's the thing. We're gonna try and stick this in the graphing calculator, but we're gonna have a few issues with it. You'll notice that if the y-intercept is going to be 100, I have a feeling that this thing 100 will be the smallest value, and so we won't be able to verify any of them. But just real quick, do our y equals. We've got x raised to the 4th, and then it was plus 29x squared, and then it was plus 100. Clearly, if this is a 4th degree polynomial with a leading coefficient that's positive, it's going to go up to the left, up to the right, and it's going to have a y-intercept of 100. So if I open my window here, I'm clearly going to have to make my x maximum or my y maximum way bigger. And so let's just make it 1,000. Why not? And then if we go by hundreds, that first tick mark will be it'll be the y-intercept. So if I hit graph, and clearly we have this shape here, it's very hard for us to see any possible issues close to the to x equal to 0, simply because we've zoomed it out so far. But at least we got what we can't verify any imaginary zeros. We don't have any real zeros to verify using the graphing calculator. All right, moving on to the next one. It says write a polynomial with real coefficients that have zeros, -3, -3, and I. And the kicker here is the real coefficients. We want to have real coefficients at the beginning, and since it has zeros, we would say that f of x is going to be equal to x plus 3, x plus 3, and then x minus I. And if I multiply this out, there would be imaginary coefficients. So we need to add a complex conjugate. Of I. And the complex conjugate of I would be -I. And so we're going to add, I'm going to put it in red here, we're going to add x plus I. And so if I is the 0, x minus I is the factor, and if -I is the 0, then x plus I will be the factor. So let's multiply these out. Oops, I wanted to have black. There we go. X plus 3 times x plus 3, well, we can do that in our head. It's x squared plus 6x plus 9. And then we've done x minus I and x minus I already. We get x squared plus 1. And so if I want to multiply these out, we'll be stacking again. So x squared times x squared is x to the 4th. 6x times x squared will be 6x to the 3rd, and 9 times x squared will be 9x squared. And then x squared times 1 would just be x squared. 6x times 1 is 6x, and then 9 times 1 is 9, giving us x to the 4th plus 6x to the 3rd plus 10x squared plus 6x plus 9. And that looks like a polynomial that has all real coefficients. So we're good there. All right, last one is similar to that one. It says find a polynomial with degree 4 that has the following zeros, -1, 2, and I, and has a function value of, and I think I need to, just let me check here real quick. I think I need to add real coefficients here. Polynomial of degree 4, and we need to have with real coefficients. I might change it before I post it to the internet, so yours might be a little different. With the following zeros, so let's make our list of factors. So I got f of x. will be equal to x plus 1. It'll be equal to x minus 2. We'll need x minus I. And so I have my real coefficients. We'll have x plus I. And so let's multiply this out. These will get x squared. It'll be minus, let's see, x times negative 2x, and then 1. So negative x, and then negative 2. And then when we multiply this one out, again, we've done it a couple times already today, so this becomes x squared plus 1. And so when I multiply this all out, x squared times x squared is x to the 4th. Negative x times x squared is negative x to the 3rd. Negative 2 times x squared is negative 2x squared. X squared times 1 is x squared. Negative x times 1 is negative x. And then negative 2 times 1 is negative 2, leaving me with my f of x currently as x to the 4th minus x to the 3rd minus x minus, oops, it should be x squared, and then minus x minus 2. And so I look at this thing and I say that that is a polynomial, sorry about that, of degree 4 that has these zeros. But the real question is, does x equal, or does f of 1 equal to 8? So let's take a quick look at that thing. So I go to my y equals, and I clear this stuff out. And let's put in that equation that we came up with. It was x raised to the 4th, and then it was negative x raised to the 3rd, and then it was negative x squared, and then it was negative x, and then just a minus 2. And if I hit graph, let's go back to a standard window real quick here. So zoom 6. And we see right here, I have my negative 1 and my positive 2 is zeros. And it looks like I've got a couple imaginary zeros that I can't see, or that, you know, they don't cross the x-axis. But when I find the value, so if I go zoom, trace, and hit value, and I plug in 1, clearly I get negative 4. So I've got a problem here. So right now, this thing right here says f of 1 is equal to negative 4. Well, I can't have that. That doesn't really help me at all. So what can I do to get that? So I asked myself, negative 4 times what number is 8? Because that's what I need it to be. And that's what I need the y value to be. Well, that's fairly easy, negative 2. So what can I do to get this thing to give me that negative 8? Well, I'm going to add another factor, and I can add this factor that is a constant, and I'm just going to add negative 2. Now, I'm allowed to do that, and why? Well, if we go back to this linear factorization theorem and on the second page, we notice that you are allowed to have that constant at the beginning. And so I can, as long as it's a factor, we set this thing equal to 0. Any of these, if I make any of these factors 0, it doesn't matter that I'm multiplying by negative 2 there. They're still going to go through the values that I want. So we're just going to bring that down, multiply by negative 2, and we'll have one more step here, multiply by that negative 2, and we'll get negative 2x to the 4th minus, oops, it'll be plus 2x to the 3rd plus 2x squared plus 2x plus 4. And that is going to be our new f of x. So this, oh yeah, it's still f of x. We can still do that. F of x here, and then this is still f of x. And so what I'm going to do is just to show you that it's okay, I'm going to do the insert here. So I'm going to go second, I'm going to do insert, I'm going to go negative 2, and then I'm going to come over here and I'm going to make this thing a plus, and then we're going to insert a 2. We'll come over to here, we'll make this a plus, we'll insert a 2, we'll come over to here, we'll make this a positive, we'll do an insert, put a 2 there, and then we'll finish it off with a plus 4. Now when I hit graph, check this out, I still have negative 1 and I still have 2 as my real zeros, but when I plug in 1, I get that 8 that I needed. So that was that extra little bit for that. Well, that's all I got for this particular lesson there, folks. So let's hit the Star Wars fun fact of the day. During the filming of the Endor scenes in Return of the Jedi, Peter Mayhew, who's Chewbacca, they filmed these scenes in the Redwood Forest of California, and he was instructed not to wander off while he was wearing his Chewbacca outfit because there was a real fear that he might be mistook for a Bigfoot and shot. That's all I got for today, folks. Have a great day. Bye.